known for quite a long time because he actually taught me how to measure things. A fun story was, so I remember actually when John first introduced this platform at the March meeting. I remember because I was the chair of the session and he had a contributed 10-minute talk. But he was so excited and I was so enwrapped by the talk that I effectively gave him an invited talk. I think he went on for like 30 minutes. You know, I think that might have been my first time chairing a session, but I think I would do it again. Anyway, so we'll get to hear now about how this platform has evolved quite a bit since then, and even into the millimeter.
If my microphone works, and I'll see if I can continue to do that same trick today, talk. If it gets to be lunchtime, just flag me down. But for the record, we're starting a little late, so it's not all my fault if I run over. Like all the other speakers, I want to thank you for putting together this workshop. I think it's great. I want to start by introducing a little bit myself, my group, and how I got into these things. This is my traditional intro slide to kind of our group at NIST, saying we play with nanofab and dill fridges and microwaves for all the fun reasons that many of us know. And the applications are primarily quantum. We are NIST, we are a metrology institute. Our group is very much on the academic end of the spectrum and for primarily quantum applications. On the slide, you can see the bread and butter is kind of good old-fashioned microwaves, the 1 to 10 gigahertz. You know, for all the reasons that we love 10 gigahertz and 10 millikelvin, you can do all the fun quantum things. What I will talk about is taking all these things and pushing in other directions, very much, as Michelle said, baby millimeter waves, little steps. We're going to go up to 40, 50 gigahertz, the wavelengths less than a centimeter. So I think the NIST lawyers will let me call that millimeter wave. But starting there, and again, seeing problems and advantages. This is the group. There's many people. There's several PIs, people like Joe Montato and Ray Simmons work with me. And as I said, a big part of the lab is bread and butter superconducting qubits. These are transmon qubits, some fluxonium qubits, these sorts of things. Another very big part of our research at NIST is using the NIST niobium trilayer process for what I call kind of the quantum adjacent circuits, the things that were just parametric amplifiers, you know, that enabled the readout, but are now also sources of entanglement, squeezed light, frequency converters, circulators, these sorts of things. And the last piece, the piece that's very near and dear to my heart, is kind of the circuit optomechanics. These mechanically compliant capacitors let you access a mechanical degree of freedom and see if that's good for anything. I will touch on how all of these things we're starting to push to higher frequencies and some of the pros and cons and things we're excited about. I'll spoil the end of my talk. Most of this is very much in progress. These are things we're just starting to see and starting to play, and that's why I'm so excited to be here. So since there hasn't been much talk about mechanics, I'll just wave the flag a little bit for what we like in kind of the quantum nanomechanics. This is one of our nano-fabricated drums. You can think of it as a circular membrane that vibrates up and down at lowish frequency, megahertz, 10 megahertz or so. We encode this in a microwave circuit. What we're interested in these are their good old-fashioned harmonic oscillators, and that's one of the best compliments I can give for something. It's a very linear, clean circuit. It's compact. It has great dynamic range and linearity. And again, most of what we'd love to do is imbue this with all the quantum control that we know and love from, you know, say the microwave domain. So how do you interact? How do you measure things? Well, let's say I had a mass on a spring. I want to know where it is. Simplest thing you can think of doing is just bounce a laser off of it. If this boundary condition moves back and forth, changes a little bit the path length, changes a little bit the phase you see. And if this is moving back and forth at 10 megahertz on some high frequency carrier, here an optical carrier, you just get phase modulation sidebands. That's my classical picture one-on-one. I will stick to that till the day I die. What we know is you can do much better. You can put another boundary condition. You can resonantly enhance this interaction. The photons interact Q times, kind of roughly speaking. And from a transduction picture, you can see it just steepens the slope. You get much more phase shift per photon. And that gives you a much better readout. But as we know, the readout also goes hand in hand with the radiation pressure forces you impart back on the thing you're measuring. And since we're going to continually use the light is in quotes, that's going to be the microwaves and the millimeter waves and in the talk throughout, it's both to do state preparation, to push back on the mechanics, put it in quantum states, and to listen. We do the circuit version of that instead of a Fabry-Perot with a movable mirror. We're going to do an inductor capacitor circuit where the capacitor is free to vibrate. And this, as many people in the field have talked about and shown, this is the exact same Hamiltonian. The interaction Hamiltonian looks like this. The A's and A daggers are the photons, the B's and B daggers are the phonons. And it's a displacement couples to the frequency of the cavity. So it's a photon number mechanical quadrature coupling. The prefactor here is a G naught, a vacuum coupling rate. That you can calculate from first principles really simply. Even I can do it for a Fabry-Perot cavity. The formula just looks like this. The overall frequency scale of this interaction rate set by the frequency of the cavity, and it's this ratio of length scales, the 0-point motion of the mechanics compared to the length of the cavity. If you want to get G naught as big as you ever can, which is what we always want to do, again, we are starved for coupling in this field, unlike the circuit QED half of the lab. You want the smallest mode volume cavity, the shortest length that you can have. And Fabry-Perot really only makes a Fabry-Perot as you go down to λ/2. So you'd be stuck with some sort of what looks like a fundamental limit. If you do the microwave version of this is a figure from Brzezinski's book. Brzezinski literally wrote the book on quantum measurement, what he calls a parametric transducer. Now, the characteristic length scale in the problem is set by the plates of the capacitor, and that can be very much sub-wavelength. So in the microwave, you take a big hit because your cavity frequency is 10,000 times lower frequency, but you can win it back with this small plate separation. The other thing to keep in mind, even if our coupling rates were very large, these systems are intrinsically very far detuned. So again, you have a low frequency mechanics and a high frequency cavity. And so they don't really interact unless there's some way to make up that energy scale. Usually what we would do, it's like what we do in other systems, you apply some sort of pump to mediate the interactions. We'll typically do red or blue sidebands to kind of couple the sum or the difference frequencies. Those are natural things that in the rotating frame of the coupled equations of motion can look quasi-resonant. And this can give you your interaction. The other thing that you get is the strength of this pump can parametrically enhance your interaction. And we use that all the time to do all the things that we like. So what's the picture? If I'm some mechanic sitting here at 10 megahertz, I'm going to stick it in a dill fridge. I'm going to get it kind of cold, but not quite cold enough. Then there's some cavity over here, and I'm going to pump at the difference frequency, for example. And now from the perspective of the mechanics, what he sees, well, there's a hot bath that looks like a heating rate. He's equilibrating with his hottish environment. But then the cavity just looks like cold dissipation. This is a phonon to photon scattering process that then leaks out and couples to a cold cavity. And so this ratio of kind of this good cooling rate, this heating rate, that defines what optomechanics is known as a quantum cooperativity. Like all cooperativities, it's a ratio of the coupling rates to the badness in the problem. Here, the badness is either cavity loss kappa or thermal decoherence. And so again, in the story of why we want to make our coupling bigger and bigger, you can see for lots of things you want to do, this is your figure of merit, goes like that coupling squared. These are things you care about a lot. And in fact, like any coupled harmonic oscillators, if you couple stronger and stronger, you can in fact Rabi flop between these two effective modes. Rabi's in quotes here. This is not one quanta at a time. If I had a huge state in this mode, it would swap that entire state over here. Again, because these are effectively linear harmonic oscillators and effectively linear coupling in the regime we're working in. So here's a phase-based picture of what kind of goes on. Let's say you start with a cold cavity and a hot mechanics, and you just turn on this beam splitter interaction. See if I can play this again. Well, you'll Rabi flop back and forth, this thermal state, back and forth between the two, but the long-term steady state is for everybody to be cold. And again, that's because you're using the cavity as your pure quantum resource. To reset, and you get this very simple, clean beam splitter interaction. Now, these microwave kind of parametric transducer circuits, as I alluded to, even though I didn't come onto these ideas by thinking about what was done back in history, looking back in history, there's a long history, primarily in the context of LIGO, before LIGO was all lasers all the time. There were really seminal work by Brzezinski. He did experiments here where he has like a rectangular waveguide and he hung a little piece of aluminum foil at the end of the waveguide. You put watts of microwave power in there and he showed the ring down time of this little pendulum can go from just under an hour to just over an hour, depending on whether you're pumping red or blue detuned. Kind of some of the first examples of dynamical back action. It was, again, in the context of gravitational wave detection. There was work by David Blair at Louisiana State. Here, they were actually levitating superconducting RF circuits. All through the 90s, there was these huge test masses that went in very cold temperatures. And all of their readout was basically what I described of cavity optomechanics, but now it's intentionally a hugely massive system because that's their degree of freedom. In the kind of early to late aughts, there were a number of groups, including work I did in Conrad Lehner's lab at Gilla, trying to use more the techniques of nanofab to have the same interaction. So all three of these experiments were little nanowires that vibrate and modulate a little bit of a capacitance coupled to some sort of CPW or coplanar waveguide resonator. Again, if we circle back to the coupling rates, well, these things had coupling rates of microhertz. Part of it is because their goal in life was not coupling, it was to measure massive objects. Here, we were really working on the coupling. We were so excited to get this up to hertz interaction rates, the intrinsics. And again, from there, you can pump and you can parametrically enhance, but that's always your starting point. At the time, across the street at NIST, they were developing some vacuum gap clean room recipes. These are to make vacuum crossovers and vacuum gap capacitors with the idea in superconducting circuits, the metal's superconducting, the dominant loss becomes whatever dielectrics you use, the loss tangents of those things. Vacuum has the best dielectric constant in the world. Let's use that. Of course, what we now know, and we knew then, you're now worried about the surfaces between these two things, but the fab techniques to make these suspended structures are kind of ideally suited for these mechanical circuits. So that's when we started making things like this. Again, this is a false color SEM image. I'll describe the fabrication because it's really straightforward. We start with a sapphire substrate. We put down a bottom electrode of aluminum. We put down a sacrificial layer that will define our drum. You can see the outline of it here. And then we put down a top piece of metal. We dice up our wafer. And then we go in with a plasma etch and we remove all of this without ever putting in a liquid, kind of standard MEMS techniques. And the crucial parameter that you can get is you can get these plate separations that at room temperature are hundreds of nanometers. But as you cool them down, thermal contractions pull you very, very close, but not touching. And that closeness, that's where we get our coupling rate from. That's the game we play over and over to try to do. So you're measuring a mode that looks something like this. It's very much like the Bessel functions you'd solve for a circular membrane. And just for scale, again, back in the frequencies, mechanics is kind of 10 megahertz. Original devices, cavity was at about 7 gigahertz. And these coupling rates, now we were excited, we were at hundreds of hertz. As I said, we can stick these things in your standard commercial dilution refrigerators. And how we just calibrate this in the first place is just to listen to the thermal motion. And if you vary the temperature of your cryostat and you measure the thermal motion just on a spectrum analyzer, the little area under the peak, if all is right with the universe, equipredition says this should be linear. And the fact that this really does fit to a line, that's our kind of in situ hot-cold load calibration for these things. What you can also see is you take your dill fridge down to 15 millikelvin, things still thermalize. That's good. That's not trivial, but you're still stuck at about 30 quanta. So again, that's why the dill fridge is still just the pre-cooling stage in these sorts of things. The thing that got me a job at NIST was showing you could turn on this sideband cooling and you could go from that 30 quanta down into the quantum regime. These are still very much things we do and love today, kind of initialize in pure quantum states, even if they are the most boring quantum states in the universe, just the ground state. And part of what we're really, really beating on is the fact that you still need to pump with kind of 1 million photons to get this interaction. That works and it's fine, but that's not really compatible with qubits and all the other things we'd want to do. So ideally, you'd want to be able to mediate these interactions with much, much smaller number of photons. And that's a bit of the theme of the talk. You can do things like sideband asymmetry. You can measure the temperature. And again, from a mechanical perspective, you get to say words like microkelvin or hundreds of microkelvin because you're controlling these low frequency degrees of freedom. These types of drums have been very good to us. We've been able to check off a lot of milestones in quantum optomechanics. These are things that have been very much done in parallel in the optical regime. Lots of experiments that Amir was involved in as a grad student and continues on these days. Ground state cooling, squeeze states, entangled states. We're NIST, so we also care very much about the measurement. How close can you get to standard quantum limits or traditional quantum limits for measuring two conjugate variables at the same time, position and momentum, or amplitude and phase of a mechanical oscillator? We also make kind of slightly more complicated circuits. By more complicated, I mean add one more mode, either one more mechanical mode or one more cavity mode. And you can do things like frequency converters. Use a 7 gigahertz photon goes to a 7 gigahertz resonator, gets converted to mechanics, and you can couple that out to a 9 gigahertz resonator. So you can do this kind of frequency conversion. You can do it very efficiently, very low added noise. And in fact, if you add more modes and more pumps, you can do it non-reciprocally. These are things we play with all the time. The last part that I find really fun is we also have non-classical sources of microwave light sitting around in the lab. So if we use our parametric amplifiers just as squeeze sources of light, you can illuminate these things with squeeze light. And looked at things like quantum enhanced sensing. Part of the power of these very, very linear circuits is you can squeeze by maybe 6 dB or so. And that's what you can get even when you get to the device through the circulators, through the loss. But then this linear mode means you're allowed to displace it by 1 million photons. And so kind of the sensing power of having a cavity state that's millions of photons with some quantum enhanced sensitivity, that's part of the fun. So I love all these experiments, but they are all Gaussian quantum states. And as I said, what we would like is universal quantum control, be able to make arbitrary quantum states and do the tomography of these states. So how do you go beyond these quantum states? Well, we know part of the answer. We know Josephson junctions are the beautiful loved nonlinearity. You can use it as single photon sources. You can use it to create GKP states, Fock states, squeeze states, whatever the kids are doing. You have full quantum control there. For example, I mean, here's some dated work from 12 years ago, just showing off some cat states they were making at Yale at the time. You have fringes of these 100 photon cat states. These days, if you take a snapshot from Serge's group in Israel, using kind of more 3D accelerator cavities, you can do thousands of photons. That's not saying this is the only figure of merit, but it just gives you the flavor of how mature the quantum control is on the microwave side. And again, that's what we're shooting for in the mechanics. It's not like we didn't try to just couple qubits to mechanics. These are all compatible with the same fabrication techniques. Here's a device from 2015 where we take one of our favorite drums, couple it to an inductor capacitor circuit, and then over here we have a qubit. And in fact, what you think you can do is program the qubit with exactly one quanta, bring it into resonance, swap that quanta into the cavity, swap that to the mechanics. Now you've initialized in a Fock state. Do that all in reverse. You now have a Fock state measurement basis for your mechanics. What's the problem? The problem is the death of all the middlemen. Because you have to move your qubit away, because it's so nonlinear, whenever you turn on your strong pumps, you do these things very serially. And that really hurts your fidelity. So in the end, all the pieces are there, but the fidelity still leaves you wanting. Other approaches are just to take circuit QED as kind of a black box quantum source, put it on the other side of a circulator so it doesn't care about the strong pumps that you do here. Yes. Yeah. So for example, if we did this protocol of create a Fock state in the qubit, transfer it to the cavity, swap it from the cavity to the mechanics, in the end, there's just a lot of loss in that process and noise in that process. We did not there. That's a good question, or these are some of the techniques. This paper we end up writing, we actually reversed it the other way. We said we're going to use the qubit as a nonlinear readout. So be able to measure the Fock distribution using the qubit was a little bit of a lower bar. So again, here you have the nice ability that your circuit QED is on the other side of a circulator, so you can pump hard on one side, but then you suffer the loss and inefficiencies of going through cables and circulators. And so you could, with very high fidelity, get the quantum state from the cavity to the mechanics, but the fidelity of the quantum state you got to the cavity in the first place was degraded. And so you can see there's superpositions of 0 and 1. Quanta here, you faithfully encode quantum information, meaning you can see the phase, but these are kind of the subtracted histograms showing the effect is there, but it's not at the level that you would want to do real quantum information. So one of the proposals we worked on with a theorist collaborator at CU, Josh Coombs, was could you use the intrinsic optomechanical nonlinearity to directly make non-Gaussian states? Again, this Hamiltonian has an A dagger A times B plus B dagger. It's not intrinsically a beam splitter interaction, so it should be capable of certain things. A theme you'll hear about throughout my talk. What we'd like to do in circuit optomechanics is take things that have been done in circuit QED. Here's a paper from Michelle's group from 2015. They took two cavities, a high Q storage cavity, a low Q readout mode, and they coupled them through a transpond. And there's a very clever scheme where you can use reservoir engineering for two photon processes. And if you do this just right, with the right combinations of pumps, from the perspective of this storage cavity, it now wants to be reservoir engineered into a cat state in something that, because of the two photon processes, can't decide if it's a coherent state to the right or a coherent state to the left, and really makes a quantum superposition of the two. We started asking, what would the analog of this look like in optomechanics? So for example, instead of your high Q storage cavity, what if this was your mechanical mode? Instead of your readout cavity, what if this is just our regular cavity, optomechanics cavity? And what if the nonlinear thing that mediates this is the optomechanical nonlinearity itself? So the picture would be something like this. Instead of applying a pump that's just red detuned to do your regular beam splitter interaction, apply a pump that's two mechanical frequencies away that now looks like there's dissipation that only happens in pairs. And if you combine that with a drive at the cavity, then the steady state of this would have attractor basins here at these two lobes. And in the right time scale, in the right snapshot, there would be quantum interference between them. Now, we're used to in circuit QED saying the Josephson interaction has a cosine Hamiltonian, and you can expand the cosine Hamiltonian to get whatever level of nonlinearity you would like. This optomechanical nonlinearity, well, it's nonlinear, but it's not clear. Where do you get these second order sidebands? So just very quickly, usually what we do is a strong drive and linearize around the drive. And that's what gives us this parametrically enhanced interaction and this bilinear interaction. The thing that I'd like to highlight that's maybe not nearly as obvious, it certainly wasn't to me, is, well, this is the interaction Hamiltonian, but you also have the bare Hamiltonian of the mechanics and the cavity. This interaction Hamiltonian does not commute with the bare Hamiltonian of the mechanics. And so if you were to expand this in a small parameter in something like a Schrieffer-Wolff transformation, you can see there are in fact higher order sidebands. Higher order in G naught, this goes like G naught squared. But now you get things that are like A dagger A times B plus B dagger squared. These are two phonon processes. And those are the types of things we're after. I always love the classical picture. Where is this coming from classically? I would say my simple pithy answer is that frequency and phase modulation is fundamentally nonlinear. If you phase modulate strongly, you get first and second and third order sidebands. These are just the Bessel function solutions that must be there. And so part of this engineering is picking off exactly the right one. So I'll go a little more quickly. Just again, the whole idea of this paper is instead of regular sideband cooling, you do this, detune your pump, and you just look at what happens. You beautifully go into these same types of things. And part of the heart of the paper is, what are the parameters you need to do this? Well, maybe not surprisingly, you need very stringent parameters. You need vacuum coupling rates of order the dominant dissipation in the system, which is kappa. This is a bar that's very high. These are things we're very much working toward. And part of what we're excited about in this paper is to see whether this is a hard threshold. Do you get no Wigner negativity until you cross this? No, but this does set the scale. This is sort of what you would want for these sort of protocols. So in the ongoing quest for G naught, again, our circuit looks like this. The G naught is really simple. It's the 0-point motion of the mechanics times this prefactor. Our G naughts have been fun and exciting, but they haven't really moved for more than a decade. And so what can we really do? Well, you can make this plate separation a little smaller. We always work on that. We always play that game of chicken and getting as close as possible. And the main reason I'm at this workshop, the main reason I've gotten enticed with going to higher frequencies is exactly the fact that this energy of the photon scales directly with the coupling. So in cavity optomechanics, there's all the work over here, all the work over here, as we know from many quantum technologies, and looking in between. What can you do? Can you take all the goodness of lump circuit elements that we love, go to higher and higher energies without having to go fully to an optical domain? I don't need to wave this flag at this workshop. I do really very much like to remind people that, you know, the Nobel Prize winning work from the Hirosh group, their photons were at 50 gigahertz. You know, these things that are kind of seminal examples of what you can do in quantum optics. The optics were 50 gigahertz. And then a lot of the work is now groups we know here very much at Stanford. I also like to point this out. Dave, when he was a grad student, worked on a first Cooper pair box experiment, and not entirely by design, but the qubit in this kind of seminal experiment was up at about 70 gigahertz. It just shows that it's possible. You know, granted, they weren't listening at 70 gigahertz, but they were actually driving at those frequencies and seeing interactions. So the idea is almost dead simple. What if you take the exact same drum and you just resonate it with a much smaller inductor? Instead of a 10 nanohenry inductor, maybe something that's like a fraction of a nanohenry. The cavity frequency should scale by a factor of 5. G naught should scale at least by that much. And for technical reasons, you might expect even other factors. And then the cooperativity would go by whatever factor you just 1 squared. That's the enticing thing. So part of what we set out to do, again, we're going to work kind of K-band, 20 to 40 gigahertz. We were choosing to do this in waveguide, not because we had to. You could still use coax, but part of it was to feel for ourselves the pros and cons with waveguide. The waveguide here isn't too big, unlike 8 gigahertz waveguide that's kind of unwieldy. These things kind of fit. So we were playing around with things like the wireless packaging. So here's one of our nanofabricated chips on Sapphire that we just put a fixed distance away from kind of a short circuit in this WR28 waveguide. Our coupling mechanism, what we do is we like to multiplex many of these inductor capacitor circuits, and we put them very close to kind of a probe feed line. That feed line picks up the electric field of the TE mode, and then we can set the coupling to each of these resonators because it's basically the mutual inductance between the millimeter wave currents in this feed line and the device itself. I like very much now that the drum itself is bigger than the inductor. In cavity optomechanics, usually your coupling rates, if you want them to be large, hopefully you should be able to see your electromagnetic mode and your mechanical mode in the same picture, in the same scale. That just says that you have the overlap that you want with these things. This is how we chose to wire our Blue Forest Steel fridge. We're still going to do the inputs down coax because we can just switch to K connectors. We're going to use a commercial cryogenic circulator waveguide. We have a chip over here. And then what we have is just rectangular waveguide going up to a commercial HEMT. As I'll say at the end of the talk, our long-term solution would be to implement parametric amplifiers. Right now, these low noise waveguide HEMTs are really pretty good. Again, from radio astronomy, people have been beating on these for quite some time. They can have an added noise of 5 quanta or so at this reference plane, and system noises of around 10 quanta or something that we get routinely, even without paraamps. And then once we've amplified more robust, we actually switch back to coax, although you could choose not to. Here's a picture of the fridge. The waveguide itself is just this single line running down the center. This is when we got the fridge, so it's not yet populated with all the other crap we stick in our fridges as well. Yeah. One of the things I'm interested in here, we tried using aluminum waveguide to bridge the gap between 4 Kelvin and millikelvin temperatures to see if we could get away with it. Spoiler alert, it's still too much of a heat load, even though some length of the aluminum is superconducting, maybe not surprisingly. Right now, we're using a stainless steel waveguide, but because it's waveguide, that's still only about 1 dB of loss. The right long-term solution, I think, would be things like niobium waveguide. These are things that we're looking into. And then on the front end, basically, we were doing all our usual setups, just putting up and down converters on the input and output. So here's our 10 millikelvin cryogenic measurement band. This is showing you at 4 Kelvin, so you don't see any of the resonances, but we have the kind of the hard cutoff of the WR28 waveguide, and we measure nicely up to 40 gigahertz. And like any setup, you can get bonus measurements out here, but things are a little less controlled where the waveguide's overcoupled and some of your connectors are over. If we take our devices and we get them at low temperature, you can now see we measure the cavity resonances that we see. We're looking at them, and happily, again, over here in the ballpark of 40 gigahertz. In fact, some of our most optimized devices actually look like this. We don't even bother to make spiral inductors anymore, just because we only need about 100 picohenries of inductance. One of the natural pros that I actually like about the millimeter wave or the 40 gigahertz is now this capacitor that was maybe 20, 50, 100 femtofarads. That's very high impedance at 5 gigahertz. That's something like kilo ohm characteristic impedance, which means you can get near there, but it's not a natural scale. At millimeter waves, these are much closer to 50 ohms. And so it helps with that constant tyranny of the impedance of free space. You're just in a more natural domain for some of these circuits. So for example, we're keeping our drum exactly the same, 10 megahertz, and just moving the cavity frequency. Here's a device at about 37 gigahertz. We measure a nice clean cavity dip from our geometry. Our kappas right now are still a few megahertz. These things are perfectly fine. That's my strong statement, they're fine. I'll explain a little bit later in the talk why we think we can make them better. They're not as high Q as we think they should be. What we're most interested in is looking at these mechanical sidebands. And here we elevate our fridge to the high temperature so we can do our calibration. We're gonna pump with a very small pump, a pump of around 1 photon. You can see we still have plenty of signal to noise, and this gives us our calibration. And what we want is about a factor of 20 in our G naught. And part of it is the straightforward improvement just from going to higher frequency. Part of it you win again with better participation ratio, and then part of it is because we've also been separately pushing on this plate separation. So this 20x improvement we're very excited about. And as I mentioned, getting system noise temperature at the reference plane of the mechanics of about 10 quanta, quantum efficiency of, roughly 90% if you want to think of it that way. And now if we turn up our pump all the way up to 400 photons, you can cool to the ground state. So now you're getting your quantum control with maybe 100-ish photons. This is more in the game where you're allowed to integrate with circuit QED without breaking things completely. And as I said, that's the long-term goal. Even if we can't run some of these intrinsic protocols for cat states, if we can have junctions around dispersively coupled that don't do anything crazy with pumps of 100 photons, you can start to have the full coupled control. In fact, if we were to do kind of the optomechanically induced transparency, just look at what the cavity dress response looks like in the presence of a strong pump that's red detuned and mediating an interaction. You get this little mechanical interference here. And if you turn up your pump stronger and stronger, you can see that you really can normal mode split. And in fact, we can normal mode split all the way until the mechanics is split by almost its entire mechanical frequency. You get, not surprisingly, your rotating wave approximation breaks down as you're pushing one of your mechanical eigenmodes up to 20 megahertz and one down toward DC. There's a fundamental instability, and the fact that you can get close to that just says we still have all the parametric coupling we want. And one of the games that people have is when you engineer bigger G naughts, sometimes you lose the ability to pump hard. And so keeping that is very important to us. Yeah, please. That is a higher order mechanical mode. That's so for the fundamental Bessel function looks like this. The next order looks like this. By symmetry shouldn't couple at all. Our symmetry is not perfect, and you can see it there. And if you were to bring this into resonance, you can see it more clearly. Yeah. Other questions while I'm paused? Otherwise, I'll keep plowing through. As I said, some of the things we're interested in are these cat state type protocols. Things we're now doing is looking at to tune the pump by 2 mechanical frequencies and look at this nonlinear interference. And you can in fact see these things now in the lab. These are things we're excited about. They're not as big as we wish they were, but they're there and they're clearly nonlinear. These interactions are no longer Lorentzian because they're not supposed to be Lorentzian. You get mode mixing here. And so understanding this and figuring out the utility, these are things we're very much in the middle of. Again, the second order processes, this scale is a G naught to the 4th. So this factor of 10 or 20 improvement in G naught is really making a big, big difference here. So how big is big enough? As I said, long term, we'd love the single photon strong coupling. In the near term, we'd be happy with just single photon quantum cooperativity, meaning still have to pump, but pump with order of photon so that everybody's happy together. And it sounds kind of weird to be able to cool your mechanics to the ground state with a coherent state pump of average 1 photon. There's nothing really that funny about it. It's still a linear process, and it's all the same equations. The last piece that we're very interested in, I've talked about the coupling because it goes in there squared. Thermal decoherence, we're really working on this. We're working on a planarized fabrication process. These are things that have been shown elsewhere in the field to make big improvements in the mechanical Q. And then the cavity Q is the thing I can't promise to come back to. So if we were to look just the intrinsic Q of our cavity at all of these frequencies, these are some of the things we didn't know. What is the aluminum devices? What are they capable of? What are two-cell level systems like? And of all these many, many devices that my postdoc and I measured, you can see we're at Qs of 10 to the 4. Nothing record-breaking, superconducting, but super with a lowercase s. And really wanted to look at what's going on here. You can imagine this could be lots of things. This could be dielectric loss, conductor loss of the aluminum substrate, radiation, vias, crossovers, all these things. So part of what we've gone to is just simpler test resonators. We're choosing spirals that look like this. Again, you can maybe as first order picture this as a lambda over 2 resonator that's wrapped up. The mode is definitely deformed from that because of the spiral, but it's a nice and multiplex way to look at resonators and just look at single layer of aluminum on sapphire instead of these kind of vacuum gap structures. When we did that, we saw Qs were a little bit better. So that was good. So that's a bit of a smoking gun saying what aluminum is capable of. We then measured some just niobium test devices, and we saw we could get even higher Qs. And this led us a bit on a sidetrack, asking, is there ways to get aluminum to behave a little bit more like niobium? Maybe as an aside, why do we use aluminum in the first place? For the mechanics, it's really beautiful. It's what we want. It's a very clean superconductor, makes high Q cavities. But then separately, it also is very light and good mechanical Q. And then lastly, and very non-trivially, it has good etch contrast for these release processes. There's lots of ways where we can stick this in an etcher for an hour or so, and it doesn't touch the aluminum because aluminum's special. These are parts of why we like the aluminum. Things I'll also say, I think we all know this here, people love aluminum for qubits. It makes some of the best tunnel junctions. Here's another quote I stole from a paper that is from Michelle and John Martinez and John Clark. They have this quote that I love. It's now sometimes said that aluminum is the silicon of superconductivity. I think these things are just true. As we also know, we look at our other elemental superconductors. So one of the things, if you just open up the cover of Van Duzer and you look at some of your favorite superconductors, you can think about what is the gap energy. These are things that Peter touched on the other day. For niobium titanium nitride, this gap can be terahertz. Niobium, it's up at 700 gigahertz. Tantalum's maybe 300, and aluminum, if it's clean aluminum, is really only 80 gigahertz. So this is part of the reasons why we're not jumping straight to 100 gigahertz. 100 gigahertz and like clean aluminum, that doesn't work. Your superconductor is not super at all. Questions we're interested in is some of the losses we're seeing because we're maybe only a factor of 2 below this. One of the things that's interesting, aluminum is weird. You can increase the gap. You can increase the gap either making very thin films. This is sort of well known. Here's a paper from the 70s. Or it's also known if you make it what we used to call dirty aluminum. I think it's more politically correct, called granular aluminum. If you oxygen dope your film, you can increase the TC of aluminum. This is a slide from Johan Pop's group. This is an excerpt from one of his students' thesis. We chatted with him a lot in the beginning and thinking about some of these things. So if you just vary how much oxygen is in your chamber as you evaporate, you can change the resistivity of your aluminum film, and the TC gets bigger and bigger, and eventually it does turn around. But you can get factors of 2 in your TC, factors of 3 if you really go to cryogenic deposition. Just for scale, the conductivity of pure silver is kind of over here. Then you get to the conductivity of platinum. And if you get over here to where you've made a better superconductor, the room temperature conductivity is more like nichrome. It's really very resistive, but maybe counterintuitively, this makes a stronger superconductivity. Again, this is from the POP group. They've been looking at this for a number of things, either as linear resonators, superinductors, kind of increasing the nonlinearity, seeing what you could have. For us, I'm interested in clean linear circuits, just asking if it can be higher Q. So we're intentionally making things thick where the kinetic inductance is small or negligible, and just looking at what the quality factors are at these frequencies. So this is our test measurements of just our regular clean aluminum we were putting down. We're now getting more reproducibly Qs of about 50,000. We did find if we made it a little thicker, we can see a slight increase. There's some frequency dependence here. I don't know yet whether we think this is real, whether this is important, but it's a fact. It's there for you to make whatever you want. And then we started making some intentionally granular aluminum. First, mildly granular, not changing the resistivity much. So 20 microohm centimeters or 90 microohm centimeters is kind of back on the same line. Not really better, also not really worse. What we have found more recently, if we go to higher resistivities and thicker, we can now get Qs that are up by an order of magnitude above this, which is 2 orders of magnitude above what we were doing. So I think these are interesting prospects. Again, for someone like myself who wants an excuse to keep using aluminum that we know and love. And then as you want to go up above 100 gigahertz, yes, of course, you're going to have to switch to niobium and other things. With these measurements, you can measure the TC in the good old-fashioned DC way. Again, this is just with the PPMS. You can see we're making the TC now above 2 Kelvin. You can also measure these things in the millimeter wave way. Take some resonance at 26 gigahertz and really look at the temperature dependence. See how you change the Q and the frequency. And you can fit the Q and the frequency to Mattis-Bardeen theory and back out a gap that's very self-consistent with the TCs. So these are measurements we're also completing and writing up. Let's see. With the last couple of minutes, I'm going to talk about some of the other things we're doing in the lab, other ways we are interested in pushing into these kind of millimeter wave regimes. Some of the work we did back in 2021, working with our colleagues in time and frequency, was asking if possibly a better way to wire your fridge instead of with tens of thousands of coax connectors might be to use a photonic link. In other words, send all your microwave signals down on an optical carrier. So let's say I take an optical carrier, I amplitude modulate it at 10 gigahertz, and then I put a fast photodiode at the bottom of my fridge. That fast photodiode now reconstitutes that sideband and gives you a microwave signal at 10 gigahertz that didn't have to go through coax cable and didn't have to go through all the cold attenuators. That's the cartoon idea. The idea of photonic links, as we all know, these are used all the time in the telecom, room temperature, classical communications, for all the reasons we love optical. It's low loss, it's cheap, it's ultra high bandwidth. Asking whether it could provide clean enough signals to drive qubits. Again, this is not quantum coherent microwave to optic transduction. This is kind of just for the drive signals, the signals that you'd want to apply your pi pulses or readout tones. Is bringing that in an optical carrier a good idea or a bad idea? I have to say, I was raised in the church of filtering. In my fridge, we want to make that the darkest, quietest place in the world. We filter the filter with filters and we shield them. So running a light pipe into your delicate, dark cryogenic environment seems like a horrible idea. Things that I'm glad we did, as we just tried it. We took a pretty coherent 3D transmon just as our test device and asked, can we drive variability oscillations in the traditional way over the coax or over an optical fiber? And for our experiment, we could not see a difference. It put a bound on, there's no badness going in at the level that we could see here. Again, the details of this paper talk about all the warts, all the things that would remain to be done. We're not ripping out all the coax cables in our fridges today, but these are still very much things we're thinking about. And as was alluded to a bit by Amir's talk yesterday, these commercial photodiodes, they can work cryogenically. They can also be ultra high bandwidth. You can make them very, very small intrinsic capacitance such that the baseband bandwidth can be hundreds of gigahertz. And so this might be a most optimal way to get 100 gigahertz signals at the bottom of your fridge, again, over an optical carrier. These are things we're collaborating a bit with to look at the pros and cons there. As I said in the beginning, other than mechanics, some of the things we work on in our group are just some parametric amplifiers. Wow, apparently this slide is autoplay ahead of me. Here's one of our NIST tri-layer chips. This is a particular type of squid amplifier where it has modes at a high frequency, modes at a low frequency, and a parametric squid coupler. This bias line, if we zoom in, actually goes to a little squid. So we can apply DC and AC flux. So what we've been using in our group for quite some time is this is our basic circuit element. Let's see if I can keep this from auto playing. Here's a zoom in of our tri-layer junctions. This is a particular type of a gradiometric squid. Here's our gradiometric flux line that comes right in that can give us strong coupling, but without being a dominant leakage path going out there. And so part of what we're interested in is, again, niobium intrinsically works well at high frequencies. Can we use this same circuit element we know and love as a nice three-wave mixing element for millimeter wave experiments? So some of these ideas that we're pursuing, again, we have a setup that looks something like this, go in on coax, look at some device under test, and we're going straight up to a waveguide hemp. You could imagine implementing some type of waveguide JPA and just pumping this Joseph parametric amplifier at twice the frequency and getting resonant gain out of this type of system. There's also clever things you could do. This is much more like Michelle alluded to the other day. These Josephson circuits can couple multi-mode things. So you can imagine having your amplifier here also be frequency translating. So you use that as your ideal mixing element that both can give you gain of your quantum information, but also convert it back down to the band that we're all set up with the infrastructure to measure so that everybody doesn't have to plumb their fridge. I think these are very, very good ideas. Everybody likes the idea of this and seeing what we can do. That's what we're in the middle of. So for example, if I were just to make a 2-mode Josephson circuit, put a mode down in the 4 to 8 gigahertz band and put a mode in the kind of 30 to 40 gigahertz band, you can then flux pump the difference frequency between these two modes. You get a beam splitter interaction, very much like the Optomechanics. So if you pump it the difference, this is now a frequency converter. So that happily moves. Ideally, if you're doing it right, it adds no noise. There would be no loss. And these are very much theory plots. We certainly haven't measured this. But again, down in the 10 gigahertz range, measuring this loss is hard to do. Measuring the noise is hard to do because to first order, they're just good. They're clean. Asking if they're at same clean at the qubit level, that's an open thing. This just moving is actually not what I would do first. You can imagine doing things like pump the sum instead. And now you'll get gain. You get 2-mode squeezing at your two different things. Or another way to think of it is 2-mode amplification. This mode is the idler for signals here and vice versa. And so if you look at the S parameters, you get reflection gain at 5 gigahertz. You get reflection gain at 30 gigahertz, but you also get kind of frequency translating gain. And this would be a way to run it. There's also many other clever schemes you can do if you want to do the frequency translating phase sensitive versions. These are things that, again, when we have a working device, we'll look at. We've fabricated these devices. For example, here's one. The low frequency LC mode is just a squid resonating with a parallel plate capacitor going out to leads that we wire bond. And these kind of antenna probes, they will actually live in the waveguide mode. And so we have little coaxes poking in. This is something that we've just started doing the spectroscopy. There are modes there, and we're not yet seeing if it amplifies. But these are what we're excited about. And in general, I would say that goes for all of the things we're doing. We spend a lot of time designing traveling wave parametric amplifiers, looking at pros and cons as you go up in frequency. One comment I will make is these tri-layer junctions, niobium is nicely superconducting. You still have to worry about the plasma resonance. In other words, the intrinsic capacitance of a Josephson junction resonating with the Josephson inductance. This is an intrinsic property, meaning it doesn't care if you make a big or small area junction. It only cares about the barrier. Our standard tri-layer process, that plasma frequency is probably around 40 gigahertz. We actually haven't measured it yet, but there's also a lot of room just by changing the thickness of that barrier. In the tri-layer process, we have robust processes that are much thinner or much thicker barriers. So in fact, what you do, if you just make a slightly thinner barrier, the capacitance goes up a little, but the Josephson inductance goes down exponentially. And so you can move your plasma frequency up above 100 gigahertz if you needed to. Again, this is very much in the future tense, back of the envelope calculation type of way. Lastly, we're also very much interested in these as squeezing entanglement sources or looking at qubits in these same frequencies. And maybe if they're not as coherent to start, they can still be good as single photon sources or detectors. In that last thing, again, I'll circle back to, for the 12th time, to things out of the Deveray lab. Michelle gave this very nice talk saying, actually, for clean readout, you really want to separate your qubit and your readout cavity by a factor of 10 in frequency. And they had this beautiful demonstration by moving the qubit frequency down. Things we're very much we're pursuing and now very much looking at in the same framework of keeping a QND measurement. Here's a cavity QED experiment. This is a regular old transmon, a transmon down at about 3 gigahertz. And this is in a very small cavity, a cavity at about 30 gigahertz. And these are things that, again, because circuit QED, you have coupling for days, you just engineer this with a G of about a gigahertz, can give you chi of around a megahertz. And these things can happily talk to each other. And those are things we're looking at. Let's see, I think that's about my time. So I won't make Dave walk me off the stage. Again, just in conclusion, I think we all agree the millimeter wave regime is kind of underutilized for quantum. Looking at how all of these different circuits play better, what the stories are. Are the modes colder? Are they more robust to temperature or noise? These are the things we all are excited about and remains to be seen. So I'll stop there and thank you for your time. Oh, I forgot the most important slide. The people that actually did the work. I want to highlight Brad Hauer. He's now an assistant professor at Waterloo. He really spearheaded a lot of these. And currently in the lab, Trevin Larson and Akash Dixit are two kind of senior postdocs pushing on these things currently. And then the whole rest of the team doing all the other things. Questions? Yeah.
Thank you for this very nice talk. You said at some point that because you are reducing the dimensions, your LC resonator is more coupled now to, it has an impedance close to the vacuum impedance. Is that this is due to the way you make these capacitances, or is this more fundamental? You're just simply the dimensions that you can make are just closer to what it would what you would need to match to the impedance of the vacuum, but also you should have more radiation losses.
Yeah. So see if I can get to a picture while I'm answering my question. So I think it's just more about saying that you're on a natural scale that makes it a little easier to not have to be as anal about parasitics. So in our original devices that look something like this spiral inductor has a characteristic impedance of about a kilo ohm, hard but not impossible. And the parasitic capacitance of this is not the dominant capacitance there, but it's still there. Now, if I go to that, those parasitic capacitance are just that much smaller and that much more negligible. That's the main reason I'm saying we win. We help. Because this same capacitor is a lower impedance that's a little more manageable, we're there. Again, I don't think we're coupling more to free space radiation because we're there. Again, we can measure that directly in this waveguide environment. That is the only way for these things to decay. And if we could have made a drum that was 10 times bigger, that would have been lower impedance at these frequencies, but that gets hard for lots of other reasons and changes many other things. So my main thought is that's kind of a natural ancillary benefit we get. And the same thing with our squid circuits in our parametric amplifiers. We use a 5 microamp junction in a squid that has a characteristic impedance at 5 gigahertz of around an ohm. Again, not impossible, but now it's actually much closer to 50 ohms. It just makes things a little more easy. I like that way of saying it. Yeah, I would agree with that.
I was just curious, what sets the loss of the mechanical resonator?
We don't know. Let's see. Things we know. The aluminum membrane is very much under tension.
Yep.
And just like people have seen in all of Optomechanics, if you put things under tension and store more things under tension, that helps your Q a lot. What sets that intrinsic loss that's there? We've actually looked very little at. Partly because we stumbled into relatively good parameters 10 years ago and haven't changed much. What the Kippenberg group has shown is if you really make a planarized process, so your membrane is really pulled in there without any of these little kinks and bumps in it, the Q can be much higher. And so whether that's about not having stress delocations or defects, I don't know. I think people are starting to understand. But the intrinsic Q of aluminum at these low temperatures, they've shown tens of millions and maybe 50 million or so. And it's not known. It's still temperature dependent, even at 10 millikelvin, 20 millikelvin, which is surprising. There's something going on. And if I had to guess, I would say the same thing everybody says. 2-level systems and mumble these things.
And what about the T2? Is there any, like, is it how?
In some of our highest Q devices, if we just look at the frequency stability, like if we go to measure on the spectrum analyzer, we can see it wandering around a little bit. That's what I would call a T2 in these resonators. The truth is that's still much, much less, even though it's bigger than the intrinsic line width, much less than the thermal decoherence rate. And so I don't think it would be the dominant limiting factor as a quantum memory. I think the heating rate coming in would still be the weakest link at these points. But these are things we can measure and continue to measure, or it's not obvious that it's always okay.
Yeah, so if you can generate any non-Gaussian state using the nonlinear dissipation engineering, what's the killer application that you can do immediately?
You can just do things that are freaking cool. As I talk to my grad students, my bar is so low. I want to make anything with a negative Wigner function, just to show a non-Gaussian state. The cat states are obviously very nice for things like error correction. We have some papers about you could make a quantum enhanced accelerometer if you put your drum in a superposition in a cat state. I don't think it's all that special that it's the cat state, but I think something that's at that same level of quantumness. So whether you did some sort of noon state or superposition of 0 and 5, I think you can see a lot of that same quantum enhanced sensitivity. Cat state is kind of a clean one we've thought about a little bit more.
Very super technical question. So for delivering the microwaves into the fridge, especially at higher frequency, so for the waveguide, have you considered still keeping like aluminum waveguide, but leaving a tiny gap?
Yeah. So we talked a lot to our detector colleagues. Again, you can do all sorts of things, put a tiny gap, and then I think what Peter showed, little shields to make sure you don't radiate out. We decided for simplicity to just go with stainless. Other things, the voltage standard used to drive the voltage standard at 70 gigahertz way back in the day. And they used to put an ultra thin layer of gold on their waveguide, enough that you can really help your microwave loss without totally killing your thermal conductivity. That's another one that's more of a trade-off than a solution.
What about like free space?
In free space, you can do little gaps. I remember seeing aimed feed horns in Amir's lab. I don't know whether he still has. Again, asking whether that on the input side where you intentionally want loss, I think any of these are viable options. And then on the output side where you're starved for every bit of efficiency, I think you'd want to avoid it.
In the interest of time, let's have last question.
I was just wondering how high a frequency you could reach for the mechanical frequency. Is there like a few hundred megahertz? Is there like kind of design direction to do this? Or?
The hardest part is to get a higher mechanical frequency, you just shrink your drum. And you can easily do that with the fab. It's just harder and harder to couple to. I would say going to higher frequency cavities helps you couple to smaller drums and higher frequency mechanics. Typically, when I look at it, if you needed me to couple to 100 megahertz mechanical mode, I could do it, but it's not clear that I would prefer to do it. that it's better in any way, shape, or form. You start colder, but you lose your ability to do all the things that you want. So whether you should, I think, is a separate question.
Hey, let's thank John for this great